Hello friends, let us now learn some important points about the X-ray production, actual X-ray generation or actual process of X-ray production. So before we go into the X-ray production, we'll see just few more important basic processes that can occur. See, this is cathode, this is anode. In order for the electrons to flow from the cathode to anode, for the electrons to excite, we need to apply a potential difference between cathode and anode. So the potential difference between cathode and anode is applied as 100 kilovolt peak. So kilovolt peak, kVp is kilovoltage peak, which is given as 100 kilovolt. The peak of potential is applied between cathode and anode. When this potential is applied, the tungsten filament is heated. Once the tungsten filament is heated, the electron from the electron shell will move outside the atom, and it will create an electron cloud, which will prevent few more electrons to exert or accelerate towards the anode, which is called a space charge effect. Once the electron gains sufficient energy, as we increase this kVp again and again, once this electron gains sufficient energy to overcome the space charge effect, it will accelerate towards the anode. And once it accelerates towards the anode, X-ray heat is produced, 99% of heat is produced and 1% of X-rays are produced. Okay. When the electrons are accelerated from the cathode to anode, they are accelerated in kilo electron volt. That is 100 kilo electron volt. So if 100 kilovolt peak of voltage is given across the tube, this will cause an acceleration of 100 kilo electron volt of electrons from the cathode to anode inside the X-ray tube. So kilovoltage peak is the instantaneous voltage across the tube. This is the tube. Across the tube, the voltage across the tube is kilovolt peak, whereas kilo electron volt is the kinetic energy of the electrons is called as kilo electron volt. So let us first learn about the processes of generation of X-rays. There are two important processes by which X-rays are produced. One, we have Bremsstrahlung radiation or general radiation. The second type process we have is characteristic radiation. So let us learn both of them in detail, which is very, very important. So first, what is Bremsstrahlung radiation or general radiation? So when the electron hits the target anode, so this is the processes that occur at this point when the electron is hit by the anode. So this is the nucleus which is present in the anode. Okay, this electron is traveling nearer to the nucleus. So when the electron passes, this is the electron. Okay, when this electron passes nearer to the nucleus of the tungsten atom, the electron has to go in this path, but instead the nucleus being positive charge, it deflects the electron from its path. That is, the electron is attracted towards the nucleus and is thus deflected from its path. That is, from its original direction. The electron is deflected from its original direction because of the attraction by the positive charge of the nucleus. So because when the electron is deflected from its path, it produces an energy which is nothing but the X-rays. Okay, now when the electron, for example, if it has 100, this electron has 100 kilo electron volts. Once it is attracted by the nucleus and it is deflected from its path, it loses certain energy and it produces X-rays. So around 50 kilo electron volt of energy is released as X-rays. So this electron will have one more 50 kilo electron volts. Now this 50 kilo electron volt energy, so this electron will now go to the second atom with this 50 kilo electron volt energy. Again, once the electron reaches nearer to the nucleus, it is deflected back. So again, when it is deflected, it gives X-ray of around 25 kilo electron volt, and the rest of the 25 kilo electron volt, it goes to the third nucleus. And by the time it reaches the third nucleus, it will again when it reaches nearer to the nucleus, it is again deflected from its path and X-ray is produced. Now this X-ray has the 25 kilo electron volt. So thus the energy that the electron has is zero. So it can no longer go to the next atom. So what is actually happening in this general radiation or Bremsstrahlung radiation is the electron, when it goes nearer to the nucleus, when it travels nearer to the nucleus, the nucleus tries to attract the electron towards it. So when the nucleus tries to attract the electron towards it, the electron will deflect from its path and it will release the energy. Some of the energy is released in the form of X-rays, and this process will repeat on and on along with other atoms, and it will release X-rays of different energy. X-rays of different energy meaning each X-ray will have different energies, and that means they can have different velocities and they'll have different wavelengths. So the wavelength of X-rays produced by the Bremsstrahlung radiation, the frequency of X-rays produced by the Bremsstrahlung radiation are different. Frequency, energy, wavelengths of the X-rays produced by the Bremsstrahlung radiation are variable. So because the in Bremsstrahlung radiation, at each point, the electron is losing some of the energy. This phenomenon is called as breaking phenomenon. There is one more way that can happen is that the electron can even directly go and it can hit the nucleus and it will lose the whole of its energy, and all the energy is released as X-rays. So the whole energy of X-rays, the whole energy of electrons is released as X-rays if the electron hits the nucleus directly. So this is Bremsstrahlung radiation. So as we have already said, the X-rays which are produced by Bremsstrahlung radiation will have different energy levels. So in our example, there is 50 kilo electron volts energy, whereas 25, 25 and complete 100 were also there. So they'll have different wavelengths. So the X-rays which are produced by the Bremsstrahlung radiation will have different energies, different frequencies and different wavelengths. So the minimum wavelength of an X-ray produced by the Bremsstrahlung radiation is given by the formula lambda minimum is equal to 12.4 by kVp. That means, for example, if 100 kVp X-ray tube can produce 100 kilo electron volts kinetic energy of electron. So when we use a 100 kVp tube, the energy of the electron will be 100 kilo electron volts. So this can produce wavelength of around 0.124 angstrom will be the shortest wavelength of the X-ray photon. That is the highest energy X-ray photon. From the highest energy X-ray photon, the shortest X-ray photon which is produced is 0.124 angstroms. So if we mark a graph using the intensity and wavelength, so the minimum wavelength that is produced by the Bremsstrahlung radiation is 0.124 angstroms, but there is a range of wavelengths which are wavelength of X-rays are produced by Bremsstrahlung radiation. Then the next type of radiation, then the next type of X-ray production is characteristic radiation. So if we summarize Bremsstrahlung radiation, simple, when an electron travels nearer to the nucleus, it is deflected from its path and energy is released in the form of X-rays, and those X-rays will have different wavelengths, different energies and different frequencies. Minimum wavelength of that Bremsstrahlung radiation is 0.124 angstroms. So the next important way of production of X-rays is characteristic radiation. In characteristic radiation, so again here this also occurs at this point only when electrons are hitting the target anode. So this is the anode tungsten atom. Okay. So when the electron is hitting, electron will travel and it will hit the inner shell electron. Okay, this is the nucleus, this is the inner shell, that is K shell, this is the outer shell, that is L shell. Okay, so the electron will hit the inner shell electron, that is K shell electron. The K shell has a binding energy, we have learned in our last class, right? Binding energy is 70 kilo electron volts. So K shell will have a binding energy of 70 kilo electron volt. So if this electron has energy of more than 70 kilo electron volt, that means think that this electron has an energy of around 100 kilo electron volt. If this has an energy of 100 kilo electron volt, the K shell electron will deflect from its path. It will hit. So as a result, this electron, then this tungsten atom electron and the K shell electron, when both of them collide, so this K shell electron will move in this direction, whereas the tungsten electron will go in this direction. That is the cathode electron will go in this direction. Cathode electron will go in this direction, whereas the K shell electron will go in this direction. Okay, so when 100 kilo electron volt cathode electron, this outside electron, this we can say has cathode electron, right? Because it is coming from the filament cathode. So when this cathode electron hits the K shell electron, both are bombarded, and as a result, the K shell electron will go in one direction, whereas the cathode electron will go in other direction. Okay, so this cathode electron loses 70 kilo electron volt energy for displacing the K shell electron. The remaining 30 kilo electron volt energy is shared between this K shell electron, which acquires some 50, whereas this cathode electron will acquire 15 kilo electron volt of energy, and they will move in two different directions. In this I wrote if the cathode electron has 140 kilo electron volt energy, if I give an example of 140, so 70 kilo electron volt energy is spent in moving this K shell electron out of its orbit, out of its shell. So as a result, the remaining 70 kilo electron volt is divided between the cathode electron and the K shell electron. So cathode electron will acquire some 35, whereas K shell electron will acquire some 35 kilo electron volt energy, and with this they start accelerating in different directions. Now there is one empty slot which is present in the K shell. Now what happens is the L shell electron, which has an energy of 11 kilo electron volt, this L shell electron will now transit to K shell electron. So there is transition of L shell electron to K shell electron occurs. So if you see, K shell electron has minus 70 kilo electron volt energy, whereas L shell electron has minus 11 kilo electron volt energy. So if we subtract the both of this energy, 59 kilo electron volt of energy X-rays are released in the form of X-rays. So this 59 kilo electron volt of energy is released in the form of X-rays when an L shell electron, when there is transition of L shell electrons to the K shell electron. Okay, so if you see the spectrum of both Bremsstrahlung and characteristic radiation, this is the Bremsstrahlung radiation which we have already seen. Characteristic radiation is not variable. See, we have particular, when L shell electron transits to K shell electron, there is release of X-rays which have an energy of 59 kilo electron volt only. Whereas when there is transition of electrons from M shell to L shell electrons, so L shell has 11 kilo electron volt of energy, whereas M shell will have an energy of 2 kilo electron volt energy. So M shell will have an energy of 2 kilo electron volt, whereas L shell will have an energy of 11 kilo electron volt. So when there is transition of electron from M shell to L shell, then there is 2 minus 2 to minus of minus 11. So that means 9 kilo electron volt of energy of X-rays are produced. So there is either production of 59 kilo electron volt of X-rays or 9 kilovolt of X-rays, or when there is transition from N shell to M shell. So that means in characteristic radiation, there is no spectrum of X-rays are not produced. There are only few bursts of X-rays are produced. So this is the spectrum of Bremsstrahlung radiation, where the wide variation in frequencies and energy and wavelength of X-rays are produced, whereas the characteristic radiations are given in the form of alpha 1, alpha 2, beta 1 and beta 2. They are bursts of X-rays are produced at a particular energy and particular wavelength. So the alpha 1, alpha 2 radiations are produced. Alpha 1, alpha 2 characteristic radiations are produced when the electron transits from L shell to K shell, and M shell, whereas beta 1 energy is produced when electron transits from M shell to K shell, and beta 2 energy is produced when the electron transits from N shell to K shell. So these are the different types of characteristic radiations which are produced. So if you see at 70 kVp, because the K shell binding energy is 70, at least the electrons should have sufficient energy to overcome the 70 kilo electron volts or kilovolt peak, sorry, 70 kilovolt peak um, of binding energy of K-shell electron of tungsten atom. So if there is less than 70 kilovolt peak, this K-shell electron cannot, so when the cathode electron has energy of less than 70 kilo electron volt, this K-shell, that cathode electron cannot replace this K-shell electron. So as a result cannot replace or cannot hit this K-shell electron. So as a result there is no characteristic radiation produced. Whereas from 80 to 150 kVp, the cathode ray electron will have sufficient energy. Cathode electron will have sufficient energy. Some 80 to 150 is more energy than 70 kilo electron would. So as a result, it hits the K shell electron and it can replace the K shell electron. The cathode energy electron will go in different direction, and this K shell electron will go in different direction and acquire the remaining energy of the cathode electron. So this is this from 80 to 150, the characteristic radiation can occur and it will produce an X-ray beam of 10 to 25% useful X-ray beam. Whereas if it's more than 150, there is decrease in characteristic radiation and there is decrease in Brahms-Stahl energy radiation also. If it's more than 300 kVp, no characteristic radiation occurs. So if we have to summarize the characteristic radiation, it is simple. When the cathode ray electron hits the K shell electron, if the cathode electron has energy of more than the binding energy of K shell of the atom, the K shell electron will uh, become free and it will go in one direction, whereas the cathode ray electron will go in other direction. This cathode electron and cathode ray electron will acquire the remaining energy from the cathode electron only. Then there is an empty slot at the K shell electron. This empty slot is filled by the transition of electron from L shell or M shell or N shell to the K shell. When the electron from L shell, M shell or N shell transits to the K shell, the difference in the energy between the L shell and K shell is released as X-ray photon. So these are the important points of how X-rays are produced. In the next class, we will learn about the intensity of the X-ray beam. Thank you.